Okay, now that we have made so much preparation, it's only natural that we can now quite easily get the distribution that we are looking for. So for that, let us look at our by now familiar picture. So we have got our original data, we have got our column space of x, and this is column space of x naught, and I am interested in finding out the distribution of ratios of the norm square of these and norm square of this vector, this vector. So norm square of this vector and norm divided by norm square of this vector. Now in order to do this, observe that we can apply our results. If I work with these subspaces, we have column space of x naught, that is the smallest subspace that we need to consider, which sits inside the pink plane, column space of x, which in its turn sits inside Rn, that is the whole space. I am working with n-dimensional data vector. This provides us with an orthogonal decomposition of entire Rn, which is given by this. I will start with my V1, which is just the blue line, column space of x naught. Then V2 will be the part of column space of x, which is orthogonal to column space of x naught. That is, if I consider this vector, this lies in V2. So V2 is column space of x intersection with column space of x naught. So it is the orthogonal complement of the blue line inside the pink plane, and V3 is the orthogonal complement of the entire column space of x. So I have written it as Rn intersection this. I could as well have dropped the Rn intersection because everything is happening inside Rn. So I have taken my green vector, my original vector, and split it up into three parts. One part is this, the projection that is lying along the blue. Then the next part is this, that is lying along V2. Then the third part is this, that is lying along V3. And all these things are mutually orthogonal, so the ideal situation to apply my result. Now, I am assuming in general that this vector, my original data vector, has the distribution x beta, is a multivariate normal, x beta mean, and variance is sigma square I. So y is x beta plus epsilon, so the distribution of y is this thing. Mean is x beta and variance is sigma squared I. Okay, so immediately I see that RSS, which is the norm square of this thing, must be a sigma square chi square random variable with degrees of freedom given by the dimension of V3. What is dimension of V3? It is n minus dimension of column space of x, which is, let's assume R, rank of x is R. So it is sigma square chi square n minus R, irrespective of whether the null hypothesis is true or false, because here I am using the distribution that is anyway given to me. That is always true. Now, if we consider the null hypothesis case, when null hypothesis is true, then the distribution is x naught beta sigma square I. So now I know that it lies here. So it lies here, and now I can say further that since it is orthogonal to that, so this vector is also perpendicular to our mu. So from here we can say that RSS naught minus RSS, which is length of this vector, norm squared, must follow sigma square chi square, and degrees of freedom will be R minus R naught, where R is the rank of x and R naught is the rank of x naught. So this is actually the dimension of V2. Observe that these are all central chi-square. Why is it central chi-square even when I have got a possibly non-zero mean? Simply because the mean is confined to remain within this V1. So here I am considering projection to V2 and V3, they are orthogonal. So after projection, the mean is completely dead. So these are all central things. However, if you are working under the general model, that is not x naught but x, in that case this still remains central chi-square, because then the mu is confined to be inside the pink plane, so it is still orthogonal to V3. However, then this part is not guaranteed to be a central chi-square anymore. This will be a non-central chi-square. The non-centrality parameter will depend on this particular relationship with mu with this particular thing. Also, these are orthogonal, so these are independent. So you can easily understand that if I divide one by the other, after appropriately scaling them by the degrees of freedom, that is, if I take this quantity, divide it by r minus r naught, and divide that by RSS by n minus r, that will be a F statistic, a central F statistic, and that will be the null distribution that we are looking for. And if your null distribution is not satisfied, in that case also we'll have a F distribution, but then it will not be a central F distribution, it will have a non-central F distribution, because the numerator chi-square will cease to be a central chi-square. So it will have some amount of non-centrality parameter. So if you want to compute the power of the test, you can do that by using the non-central F distribution.